We have a very important concept, the derivative for all calculus courses. We will now make use of the limit concept developed in first three section of the chapter 2 to solve the two important problems illustrated in this figure. The solution of each of these apparently unrelated problems involves a common concept called derivative. First of all, let's talk about the rate of the change. If you pass mile marker 120 on the illustrated highway at 9 a.m. and mile marker 250 at 11 a.m., then the average rate of the change of distance with respect to time, also known as the average velocity, can be calculated easily. Okay, in the highway at the time 9 a.m. Here the kilometer is 120 miles, and when you are at that point, the time is 11 a.m. and the kilometer is 250 miles. So change of the position or change of the distance easily can be calculated by these differences. When you divide the assumed time, so you find the average rate of the change of the distance with respect to time. So which is 11 minus 9. So this ratio gives us the average rate of the change of that situation. This is 65 miles per hour. Of course, your speedometer reading, that is the instantaneous rate of the change or instantaneous velocity might well have been 75 miles per hour at some moment between the 9 a.m. and 11 a.m. Sometimes 50 miles per hour. Okay. We will define the concept of average rate of the change and the instantaneous rate of the change more generally, and will apply them in situations that are unrelated to the velocity. Thus, we can define average rate of the change as the following way. Let's write the average rate. Rate of change. So for any function y equals f of x, the average rate of the change, the average of the f, equals average of the from x equals a to the x equals b. Okay, f of x, f of b minus f of a over b minus a, or this is from the average from x equals a to x equals b. We can write also this one from x equals a to x equals a plus h. Average value of the function, average rate of the change of the function f is f of a plus h minus f of a over h. This quotient is very important. By using this quotient, we will define the derivative, okay? But now this is just definition of the average rate of the change. So note that the numerator and denominator in this function, in this equation, are differences. So this quotient is a difference quotient. It's called a difference quotient. Okay, to understand the physical idea behind this definition, let's look the following example. So the velocity is related to velocity. A small steel ball dropped from a tower will fall a distance of y feet in x second as given approximately by the formula. Y equals f of x which is 16x square. Okay, so show figure 3 shows the position of the ball on a coordinate line, positive direction down, and the end of 0, 1, 2 and 3 seconds. Okay, so here the figure that's for this situation. So when x equals 0, x represents the time here. When x equals 0, position as a starting point here, okay? Small steel ball is here, or actually here. So after 1 second, position at when x equals 1 second, y is 16 times 1 square, so 16 feet, okay? So this distance is 16 feet. So from 0 to that point, it is 16 feet. If x equals 2, the position is 16 times 2 square, so this is 64 feet. So this distance is 64 feet. And when x equals 3, you can calculate this is 144 feet. So this distance is 144 feet. So this is the ground. So find the average velocity from x equals 2 seconds and seconds to x equals 3 seconds. Okay, so let's give the response for the part A. What is the average velocity? Actually, velocity is the rate of the change of the position. So here y is the position vector, position function. Okay, so velocity, the average velocity means average rate of the change of the position. So that's equals average equal distance covered over elapsed time. So which equals from 2 to 3. When x equals 2, this is 64. But first we should calculate x when x equals 3. When x equals 3, this is 144. So 144 minus 64 over 3 minus 2. Maybe we can emphasize this is f of 3, that is f of 1. So this is average rate of the change of the function f from 2 to 3. So that's equal 80. Yes, 80 over 1. So this is 80 feet per second. So this is average velocity, okay? We see that if y equals f of x is the position of the falling ball, then the average velocity is simply the average rate of the change of the f of x with respect to time x. Okay, let's continue from part B. In the part B, find and simplify the average velocity from x equals 2 seconds and x equals 2 plus h seconds. Here h is different than 0. So the average velocity equals, maybe you can develop by the v, velocity average. Velocity average means, okay, actually this is average velocity. Average velocity. Okay, so this is f of 2 plus h minus f of 2 over 2 plus h minus 2. So this equals f of 2 plus h 16 times 2 plus h square by using this function, but this is not 2 plus h square, that one, 2 plus h square minus 16 times 2 square over denominator is h. So which equals 64 actually 16 times 4. Maybe you cannot follow. So this is 4 plus 2h plus h square minus 16 times 4 over h. And easily you can observe these terms cancelled with the 16 factor. Then that equal 32 plus after cancelling the h term, maybe it's the first right, 32 plus h plus 16h square over h. Then this is 32 plus 16h. Here h is different than 0. So notice that if h equals 1, you can find the answer in the part A. The average velocity is 18 feet per second. Okay, from here you can calculate easily. This is not 30. This is, sorry, because this is not 18, so it should be 64. Yes, because our mistake at that step. This is 4h. Now it is okay. So this is 64. Now let's look to part C. Actually, find the limit of this expression from part A when h goes to 0, if limit exists. So we should look to this limit. Limit h goes 0, 64 plus. Okay, first of all, let's write the quotient. F of 2 plus h minus f of h over h. So this limit, we have already calculated. This quotient equals 64 plus 60h. So when h going to 0, 60h goes to 0, so this is 64. So this value will be called the instantaneous rate of the change, or instantaneous velocity. And also it is called the derivative of the function f at the point 2 in the future. So in the part D, discuss the possible interpretation of the limit from part C. So what we can say that the average velocity over smaller and smaller time intervals approach 64. So because h goes to 0. Okay. So let's write the average velocity over smaller and smaller time intervals approach 64 feet per second. This limit can be interpreted as the velocity of the ball at the instantaneous that the ball has been falling for exactly 2 seconds. Okay, actually we don't have a space. That's okay. Let's continue. So this limit can be interpreted as the velocity of the ball at the instant that the ball has been falling for exactly 2 seconds. Therefore, 64 feet per second is referred to as the instantaneous velocity. So this is called a instantaneous velocity at x equals 2 seconds. Okay, and we have solved one of the basic problem of the calculus now.